I guess I've learned something because I understand a little more of this now than I did. The reason that we care is that fundamentally hitting the stack, return to libc, and hitting the heap, in addition to format strings and of course the whole user-based, and user-based exploit stuff, which is a whole different can of worms, but as far as targeting kind of memory corruption vulnerabilities, that's still those are still the main approaches. It's just we've sort of fine-tuned how we do it. This is National Vulnerability Database, remote buffer overflows, up to 06. I know that there's some questions about how these stats are gathered and everything else, but I think that the main thing that we can agree on is that the problem hasn't got a whole lot better, and we've continued to see remote overflows as one of the more common methods of remote exploitation. So, at a very high level, and I know there's going to be errors in this, and you could probably pick it apart, but at a very high level, you're taking a unchecked allocation of memory somewhere. You're inserting input, and you're targeting either the stack or the heap, preloaded functions in memory. You're moving execution flow to take advantage of what you've inserted into memory, and then that allows you to control execution flow. So that's fundamentally the problem. So the first kind of approach to this, and going back to some of the von Neumann model and the data code separation stuff, the first kind of approach to this was the no exec stack. And fundamentally what that does, we'll get into some of the specifics of how some of the approaches work, but at a very high level, what you're doing is you're creating a data code abstraction, say kind of going back to von Neumann, and you have instructions and you have input and data. You're separating those out, and you're creating a wall between them. Essentially the problem here is that if you have unchecked input, that then allows you to insert instructions, and then you jump to those instructions. That's what a stack-based overflow does. So actually, a little bit before some of the emulation stuff, you had the no exec stack bit in Solaris. If anybody was worked a lot with Solaris, I did a lot with Solaris in the 90s. We used to always congratulate ourselves on that. Yeah, we've got a no exec stack. All the hardening scripts and things like that would always set that bit. And it's like, hey, we're safe. We're great. So HPUX and some of the other Unixes also had similar implementations. Nowadays, we have the NX bit, which is kind of rewinding back to that same principle. Part of this is related to the fact that on 64-bit architectures, you have better memory management than you do on a 32-bit arch. So you have the page address extension, gives you an ability to separate memory pages in a more granular kind of way than you do on 32-bit, where it's more kind of a blob. Something to point out is that all the different implementations of NX or XD or anything else, whatever you want to call it, require you in the operating system to take advantage of that bit. It's not something that just sort of runs by itself. And we'll get to that in a minute in terms of how that's applicable to some of the methods to circumvent it. The emulation software stuff is an approach to kind of get the same thing on an IA32 platform that's not as granular as 64. You have the WXORX stuff in OpenBSD. ExecShield is a Red Hat technology, and then there's PAX and DEP, which is the Windows one that probably most folks are familiar with. They are less fine-grained. There have been some things that talk about taking advantage of the fact that it's not quite as granular. If you run into, as I understand it, if you run into something where you have memory allocations that are a little bit smaller than what you can kind of break down easily into two segments, sometimes the software implementations will exempt themselves and say, okay, I'm not going to actually take advantage of the separation. And there have been some exploits that take advantage of that. But on 32-bit, it's something, and it's more than what you have without it. One of the things that you run into with no exec stacks is that it's problematic for applications that want to construct code on the stack. JIT compilers, Java, .NET's Java runtime, anything that does emulation and things like that, they're gonna expect to have that functionality. And where that gets interesting is that what that has meant is that in a lot of the platforms, they've had to build ways to opt out and exempt yourself from that. And so some of the attacks have taken advantage of that. And so sort of on to the attacks against no-exec. The vulnerability is still there. You've basically reduced it down. You've removed sort of one vector and one method of exploitation, but you haven't removed the vulnerability. And you've simply just made it a little more difficult to exploit. So return to libc, we talked about that earlier with Solar Designer. Most of the talks I found on OwnDep or OwnNX, they all talked about a lot of different stuff and made it sound a lot more complicated than it really is. But fundamentally, what most of those are about is return to libc. Just calling an existing preloaded function, something in memory, as opposed to actually inserting shellcode. One of the other things which I was actually talking to somebody about earlier, Dave Litchfield has done some work with doing return to libc, calling mprotect, and mprotect is a function that allows you to say, kind of leave my stuff alone and exempt yourself out of the model. So it's possible to do return to libc and then jump to mprotect and insert things onto the stack, and then they're left alone. It requires, with return to libc, a known address, a useful function in memory. We always kind of refer to it as return to libc. It's typically return to system, return to winexec. So we're just calling functions that run code that are in the kind of the standard runtime libraries for a given OS. Heap-based overflows, no exec stack doesn't apply. Fundamentally what you're doing with a no exec stack is you're just saying this specific set of conditions, which is I'm inserting data and I'm jumping to it, or inserting code into a data segment and jumping to it. So it doesn't do you any good on the heap. It doesn't do you any good with return to libc. Justin of Bioactive did a talk yesterday on DL Malik. There is an Atlas talk if you're going to DEF CON that's also on heap exploitation that is probably of interest. And there's the Ollie Whitehouse talk, which talks about some of the specific ways that Vista does heap allocation stuff. One of the other ones that I found was an academic paper by Piramposa and Embody, and I guess Embody did a talk here. I think they're from UMich, if I'm not mistaken. But the Hannibal attack concept that they came out with was to insert a pointer in a vulnerable segment for some arbitrary address somewhere, and then as the second step, insert your payload, and then get execution to jump to that payload. The thing about that is, what it doesn't do that a traditional stack-based overflow does is take data and jump over to code. So again, the NX just becomes, Dave Maynard called it a couple of years ago in his talk on DEP and NX a speed bump. It's just enough to make it just a little bit trickier. But actually, if you look at exploits today, as more and more platforms have no exec stacks, and in fact, I would say that pretty much everybody at this point in the past 2 years has some kind of stack execution, implementation that prevents that. It's been not a barrier at all. People have sort of engineered around it and sort of expected it. If you look around Millworm, there is a guy in South Korea, who has a whole bunch of papers about dealing with Red Hat's exec shield, and he's sort of perfected it. So Red Hat is, a pretty solid no exec implementation on Red Hat Enterprise 4, and so just about every kind of stack-based vulnerability, he's just jumped right through their exec shield implementation. This one was kind of interesting to me. Escape and Skywing did a paper on MS's step. Something that MS does with their no exec implementation that's a little bit different is that it's a runtime flag. So it's in memory, and for a running process, you're setting some bits to define whether you're executable or not. So what they found was that you could flip those flags and then again, this was sort of via return to libc. You could then flip those flags for something that's vulnerable and then take advantage of stack-based overflow. So it became just totally irrelevant. The point of that, if you have, and this isn't something you can necessarily do on a desktop, but if you have Windows-based servers, go into your boot INI. It's documented by MS, but it's not something you can do in the GUI. Go into your boot INI and set no execute equals always on, and that means there's no opt-out to it. Basically, the other two options, which are all Windows services or on by default but allow apps to opt out, that process execute flag is what you're setting when you say opt out. So if that can be controlled on the fly, it's really irrelevant. PAX is another no exec implementation. They do this in a file header, so they have some bits in the ELF header that give you a way to set that. Potentially, I think that might be a higher bar and kind of a better middle ground to allow you to exempt things that don't get along with no exec stacks, but still have a little better protection. Some more opt-in, kind of opt-out ugliness. Everybody's implementation allows you to disable checks at runtime or in compile time. Virtual Protect and mprotect both give you the ability to set particular areas of memory as being exempted from the model. Skywing has, related to that same paper, he has a no exec Hall of Shame. I've kind of found this too in running with no exec stack without the, in Windows without the option to opt out of it, that lots of things that you wouldn't expect to crash will just blow up. So personally for me, Firefox, Acrobat just die just all the time. And I'm sure that it's because they're making an mprotect call somewhere and then it's falling over. Something that I actually stumbled across as far as no exec stacks was a number of years ago I was running an app called Secure Stack, which is a add-on for Windows. Actually at the time it was NT4 that does a software-based no exec stack on Windows. And I had a backup guy, admin guy that pushed backups, a backup administrator, and he was trying to do a code update to backup exec, and it crashed all the boxes running the agents because he had the secure stack stuff. And what was interesting about that was about maybe 2 years later, there was a stack-based overflow in backup exec. So, I kind of wonder if the things that break maybe be breaking, they may be breaking for a reason. So kind of the next step was to go to canary-based stuff and look at checking for corruption of memory in the stack itself. StackGuard was the first approach, and this was Crispin Cowan, who's also the author of AppArmor. What you're doing is putting a canary value somewhere in the stack for the return address, and when the canary value changes, that means the return address has been overwritten. Later versions, he added some more features, and actually there's StackGuard, PointGuard, I think there's HeapGuard, FormatGuard, I know there's. So they kind of started adding a lot of other stuff, but the main problem with the Munich stuff was it was very x86 centric, so it didn't really get picked up by a lot of other things, and it didn't get integrated as a whole into GCC. Which brings us to ProPolice. Very awesome stuff. Hiroki Ito of IBM was the author. The OpenBSD guys did a lot of work with it in later years. It was integrated into GCC 4.1, so this is now available in GCC for most of the major Linux Unix distros that have moved to that. So like Red Hat 5, the latest Ubuntu, and things like that are using GCC 4.1, and they do have a ProPolice implementation.